Dr. Jacob Koruth is going to talk about the new insights into arrhythmia mechanisms using a high-density multi-electrode mapping array.
Thank you very much. I want to take a moment to thank the organizers for this very kind invitation. You already heard the topic for today. These are my disclosures. So when I think about complex arrhythmia mapping, a few very obvious things come to mind. First and foremost is entrainment mapping, which is primarily the way we approached and tried to assess what parts of the chamber were relevant to the arrhythmia. But what has changed over the last many years, as many of you use in clinical practice, is combining scar and substrate mapping along with activation mapping. And what this means in 2018 is high-density multi-electrode maps. Really, all systems now have promoted the utility, and we've all begun to see that we now understand arrhythmias much better. The very definition of high-density map has changed and evolved over time. Gone are the days where 50 and 500 points were high density. Now we're talking about many thousands of points. But what is critical for success is to rapidly acquire these points and automatically annotate the EGMs. This allows us a unique combination of understanding simultaneously the substrate and drawing attention based on the substrate to isthmuses that allow us to ablate and terminate the arrhythmia with minimal RF, but with durable lesions. Now, all of you know there are several factors affecting size and shapes. Here's a long list of them from this paper from Dr. Josephson and Dr. Anta. But the important ones that I'd like to draw your attention to is the direction of activation, and more importantly, the direction of the sensing bipole. And as Dr. John Day mentioned, this particular grid catheter takes advantage in the current software version of this particular advantage, that it looks for every point in two orthogonal directions. So if you have no voltage in one direction, it'll look in the other direction, and this is the voltage that it's assigned for that particular point. This is called the best duplicate approach. And what is the preclinical evidence for the importance of electrode orientation? I'd refer you to all the papers by the group led by Nanth Kumar that demonstrate, and I've just shown you one image from the atrium demonstrating that when you're just looking at vertical and horizontal placement of the bipole, you see a 2 millivolt increase in sinus rhythm and a measurable increase in atrial fibrillation. Now, their work goes much further than just orthogonal bipoles. They go on to look at a different paradigm of omnipoles that is currently not available with this catheter, but nonetheless, today's use of this catheter makes use of this particular advantage. So this is just an example that was addressing one of Vivek's questions, which is how do you use the catheter? The catheter is flat, so it has to be swept along the surface of the PV to create anatomy. So that's a learning curve for people who don't use this catheter. And in my mind, the advantages really surround, besides it being a multipolar catheter, the increased sensitivity in picking up EGMs, as was pointed out. So your chances of overestimating scar in a complex arrhythmia is much lower. This therefore facilitates voltage-guided approaches. So what are the voltage-guided approaches that people use? We heard about sinus low-voltage substrate ablation in non-paroxysmal cases. And in our lab, in complex arrhythmias such as atrial fibrillation, one approach that some of us use is to look for fractionated signals that occupy a significant portion of the cycle length in regions of low voltage area and ablate them in an attempt to organize arrhythmias. And finally, in future iterations, we'll have the availability, hopefully, of the omnipolar approach that has even more advantages in picking up the larger voltage and non-activation dependent assessment of wave direction.